welcome to part 2 of the review of the first homework set. In this part I'm gonna go through 3 questions from chapter 23, namely number 20, 23.20, 23.52 and 23.55. Alright, so I've started by drawing the setup for 23.20. If you haven't read the question again, make sure you open your Mastering Physics or your textbook and have a look what the question says. The idea is this: we've got 2 sheets, one here, and both are charged up with a certain charge density on their surface, meaning a certain amount of coulombs per square centimeter, essentially, or square meter. And we're asked to find the electric field strength on one side of them, in the middle between them, and on the far side of both of them. Now, the one piece of information that you need is that the electric field strength, due to a big sheet, and big just means, it's ideally infinitely big, but it could just mean, big enough that compared to the distance you are from the sheet, it almost seems like it could be infinite. Essentially, that the dimensions of the sheet are a lot bigger than your distance from it. And then the electric field strength is going to be the charge density, this is eta 0 in this question, divided by twice epsilon naught, this constant. That's there's a different way of essentially writing the electric constant. Remember that K can be written as 1 over 4 pi epsilon naught. So it's just a different way of writing K, right? This is just a numerical relationship. But this way, writing things in terms of epsilon naught turns out to be more useful once we get away from just using Coulomb's law. And in this chapter, if you read through it, this is derived by an integration, right? You essentially split your sheet over a large number of tiny chunks, and you work out what's the contribution to the electric field due to each chunk, and you add them up. Adding an infinite number of infinitesimally small contributions is what integration is, and you come to this result. In chapter 24, when you discuss Gauss's law, you're going to get a more effective way of doing some of those calculations, including this one. But either way, for the purposes of this question, right, finding the electric field is just something we assume to be a known result. Notice the electric field near a large sheet is just straight towards it or straight out of it, right? Towards it if it's negatively charged, going out when it's positively charged. And it doesn't get weaker as you get further away. At least not for an infinite sheet. Or if it's not an infinite sheet, if it's a finite sized sheet, at least it's approximately the same as long as you stay close to the sheet. So it doesn't fall off with as 1 over r or 1 over r squared or anything like that. It's just a constant strength. Alright, so we've got this result, and now to figure out what happens when we have 2 sheets, we just add the 2 electric fields. Right, so this one, the sheet that has a charge minus eta 0, and that is just some given value, some constant value. The electric field points inwards, and this is the field strength. The second sheet has 3 times the charge, 3 times the charge density, 3 times the amount of charge per square centimeter of sheet, and it's also positive. So here the field lines, they come out, point outwards, and they're denser. I've tried to represent this here. There should be 3 times as many lines here as there are here. Not sure if I got it exactly right, but you get the idea. So now I want to know what happens if I'm on the very left, 0.1, in the middle, 0.2, or out here, 0.3. Let's look at 0.1. Right, 0.1 is here, 0.2 is here, 0.3 is here. At 0.1, the field up here, the field from the negative one points to the right, the field from the positive one points to the left. So that means when I add them, I'm getting this, and then I add to it this. Oops, you can't see this. Move the paper up, right? This is from the 3 eta 0 chart sheet. This is from the -1 eta 0 sheet. Oops, wrong around. I'm being crazy here. You're doing it the other way around. Excuse me. This one is this way, and this one is this way. And so what you end up with is essentially just this way. And the value here is going to be, well, this one, that's the one to the left, minus this one here, it's the one to the right, right? Because the fields point in the opposite direction. So I subtract one from the other. The bigger one wins, right? This one wins to this one, like the final field is to the left, but it is weaker by this amount. So here, the field is going to be just, the field strength is twice eta 0 over 2 epsilon naught. This here minus this here. In the middle, right, so now we're looking at the point that's in the middle between the two sheets, well, both electric fields in the middle point to the left, so they just add. So in this case, I get this one plus this one, right, to get a stronger field, so that's going to be this one. So here, the electric field strength, I guess I'm just talking about the magnitude here, is equal to 4 epsilon naught. Sorry, eta 0 over epsilon 0. So epsilon naught, right? This one here plus this one here. They add because they're in the same direction. And then for the final one, well, now the field due to the positively charged one, the stronger charged one, is to the right, but the one due to the weaker negative charge is to the left. So I'm gonna do it like this, and so I end up with, well, the longer one still wins, but again I have an electric field strength that's just 2 eta naught eta 0 over epsilon 0. Oh, 2 epsilon 0, excuse me. And in this case to the right. And that's what we were asked in this question, 23.20. Okay. So let me move on to 23.52. So 23.52, again, make sure you're looking at the question first so you know what it's about. It is essentially a projectile motion problem. The setting is something like this. I've got a positively charged plate down here and a negatively charged plate up here. And if they're equal in charge density, this is sort of a setup that you might get from what's called a parallel plate capacitor. You've got opposite but equal magnitude charge with two sheets, and the result is that you get an electric field on the inside that essentially points straight up and is constant throughout. Okay, and now we're going to place an electron, I believe. Let me double check. Yes, we're launching an electron from somewhere here by some mechanism, right? We're giving this some initial velocity, let's call it v0, at some initial angle theta. Now, as long as the electron is anywhere between the two plates, right, there's going to be a force on it. The force on the electron, right, is that F on electron, is going to be equal to E times the charge of the electron. right? But the electron charge is minus, so this is going to have a minus sign with it. Suppose a better way of putting this is that it's going to be downwards. So let me write it like this: E times E down. Right? I'm trying to eliminate any sort of ambiguity about signs or what does it mean, what's positive, what's negative. No. I look at a situation and I can decide right away, okay, it's an electron inside an electric field. The electric field points up. The electron is negatively charged. Therefore, the force is down and it has this field strength, the strength of the electric field itself times the charge of the electron. So that means I've got no force in the horizontal direction, so it's going to go at a constant speed, constant velocity in a sideways direction, and I've got a constant force and therefore constant acceleration in the vertical direction. And that makes it a projectile motion problem, right? It's not falling under gravity, it's falling under a constant electrostatic force, but that doesn't change the kinematics, as it were. Let's work out what the kinematics is. We have an x direction. Let's label those. So I'm going to go with the usual. This is my x. This is my y. I'm going to have in the x direction, I have the distance traveled in the x direction is the velocity in the x direction times the time interval. But what is this? Well, it's going to travel with a constant velocity, so whatever it has initially, that's the horizontal velocity it's going to keep, which is v naught cosine theta times delta t, right? You solved lots of those kinds of problems early on in your 161 course. In the y direction, well, what we know is the change in y is given by v naught sine theta, right, the vertical component times delta t, but now there's a constant acceleration, so if we were to add 1/2 at squared, it's 1/2, what is a? A is going to be force over mass, right? We write this down. A y equals, if y is up, then the acceleration is down, force is down, divided by the mass of the electron. That's something you can look up. I'm going to plug this in here. A minus e little e over the electron mass, so electric field strength, times electron charge over electron mass, times delta t squared, right, the constant acceleration situation. And what we're trying to find in this case is we want to find the electric field strength given that we know how far the electron travels. Alright, so it's going to follow this sort of path like this. And we know the range, so we know this value here. In the book it's 4 centimeters. We are given the initial speed and we've got the angle. So we can use this to find the time. We plug the time in here. We know that at the end of its flight, right, that's the time period we're investigating. At the end of its flight, its displacement is 0. So that means we can then solve for E. Let me just write this out. From this one here, I'm going to get the delta t, right? We don't know from the beginning how long it's in flight, but we can write this as delta x over v naught cosine theta, and those are all known. Right, this thing here is let's call it the range. Those ones are obvious, right? So then plug this into the equation for delta y. And note, delta y is 0. This is something you should obviously know from 161, but maybe it's been a while, so this is a quick reminder. You can't forget anything in physics. Delta y is 0 because it ends up at the same height as it started, and so you can then solve the delta y equation for the electric field strength. This is part A, right? I'm not going to work through this. You can do this. This is basic algebra. For part B, this whole thing was A. I guess this was a general setup. Let's say this is A. For part B, we are asked to find the minimum separation of the plates. In what sense is that relevant? Well, the idea is if this thing goes too high up, right? If the plate were, say, here, it would hit the plate. Like, it would never complete its arc. It would hit the negative plate. So, really what we have to find is what's the highest point of the path. Find highest point of trajectory. So, how do we do that? Well, again, you should know this from, days gone by, but just in case you forgot, at the highest point, you have that the velocity in the y direction is 0, and we know that the velocity in the y direction is your starting vertical velocity, v naught sine theta, minus the acceleration times the time. And you can use that together with the other kinematics that you've worked out to figure out what is the highest point of your trajectory. And then the statement has to be that, well, those plates better be at least as far apart, or realistically at least that far apart plus a tiny bit, so that the electron does not crash into the top plate. Again, I trust that you can finish this off if you didn't get it in your original homework. The last question I want to do is 23.55, and that wasn't actually on your homework set. It's a question concerning circular motion. You had others on your homework set from circular motion, in particular 23.58. But I think 23.55 is a little bit more interesting, because it has a little subtlety about it. So if you haven't looked at it yet, please make sure you read the question before you continue with this video. So the setup for 55 is you imagine you've got a positron, which is in a particle much like the electron, except its charge is positive, everything else is the same. And you have an electron, and they circle each other. So the idea is something like this. You've got an electron here, you've got a positron here, and because they're oppositely charged, right, P here is positron, not a proton, so the force is going to be inwards for both of them. And if they, if they're set up right, they might just have just the right speed to sort of go around each other in a big circle. I'm bad at drawing circles. This is meant to be a circle, right? So let's say there's some distance apart. Let's call this distance r. And in the question, this distance is given as 1 nanometer, right? 10 to the minus 9 meters. I presume that's a realistic value. And we're asked to find the frequency of the rotation. Now, let's just think physically first. Why is the frequency determined by the setup? Well, if you imagine them going too slowly, right, then they would just start moving towards each other and crashing and meeting in the middle. Or maybe they'd just loop round each other right in the middle and then go on some elliptical orbit or something like that. If they're moving too fast, you could imagine it's going super fast this way, this going super fast this way. The force between them, the attraction, might just not be strong enough to keep them together. So this one might sort of shoot off this way, this one might shoot off sort of like this, and that's that. But to go in a circle and you're going to continue to do so, they need to go at a very precise speed. Let's figure out what that speed is, and then use our insight from finding the speed to find the frequency. So what's the physics here? Well, the thing that keeps them in a circle is the electrostatic attraction. And it doesn't matter which one I'm picking here, the force between them, the attractive force, is going to be equal to K, charge of one times charge of the other. So in this case it's just E squared, because remember the charge of the electron is minus little e, or minus 1.6 times 10 to the minus 19 coulombs, and the charge of a positron is just the same thing but with a plus sign instead. Divided by the distance between them, the distance between them I called capital R, and that is squared, right? This is because we know that's the only force acting. But then that better be equal to the force needed to keep them going in a circle. That means this force acts as the centripetal force, right? Remember, the centripetal force in circular motion, that is the force that stops something from just going in a straight line. It's the force that always points inward, always turns it, but never speeds it up or slows it down. Well, this force, right, it's not a force that's there in addition to other forces. We identify, okay, the electrostatic attraction between them acts as the centripetal force. It's centripetal force, that's a role a force takes on. Right, that's equal to the mass of the electron, or the positron, same mass, right, they're identical, except for the sign of the charge, times v squared over r, the centripetal acceleration. And if you don't remember where this comes from, then you should go back and look at your notes from when you first covered circular motion, somewhere in your 161 course. Now, notice the separation between them, r, big R, is not the same as the radius of the circle, right? Now, this is the subtlety here. If you had, say, an atomic nucleus, and you've got a little electron that goes around in a circle, then the radius of the circle is the same as the separation between the electron and the nucleus. Because the nucleus is heavy, it essentially doesn't move. Well, in this case, the situation is different, right? The separation between them is the diameter of the circle. If that goes into here, that determines the strength of their electrostatic attraction. But what goes into here, right, this comes from the path that this object is taking. So this is the radius. So put the center is here, right, and this is r, and we have that r equals 2r. The separation, the diameter, is twice the radius. Fairly basic, but you only see this if you actually, you carefully draw it out. You make sure you understand what's going on, and that this is from the trajectory, the circular motion. This is from the physical separation. So what that allows us to do, because this is known, right? Those are sort of physical quantities determined by nature. What this allows us to do is we can you rearrange this. I'm not going to do this, you can do this yourself. you find v, and having found v, we can rewrite v, right? V, I guess we write like this, then use v is, well, the speed, right, of something going in a circle is the distance traveled over the time taken. 2 pi r, little r, the radius, not diameter, not the separation of the two objects, divided by t, where this is the period, the time for going round once all the way. And I can just rewrite that as, let me do it down here, 2 pi r times the frequency. Because frequency is 1 over t, right? If it takes me half a second to go round, 1 over half is 2, it goes twice round per second. If it takes me 5 seconds to go round, so 1 over 5, my frequency would be 1/5. 1/5 rotation per second, and so on. Right? This is this relationship. Hopefully you remember it. In case you don't, right? Here it is again. And that then solves our problem. Use this to solve for v, paying attention that this one is 1 nanometer, so this one, little r, is only half a nanometer. Having found v, you can use v to find the, well, just find the frequency directly, right? Because you know r, so you can just solve for f. This is kind of a cool problem because, among other things, it's a problem that is much more general than just involving an electron and a positron. It's really just you've got two objects of the same mass that attracted to each other. So what we could have two balls with a spring between them and we make it spin. Then this would be something else. It would be the spring constant times the stretch of the spring, but, you know, same idea. The setup is the same. Or something that's very much analogous is, imagine, let's say, a binary star system where you've got two stars, two suns, of the same mass. I guess that'd be a coincidence, but we could imagine that kind of thing being out there somewhere in space. The same mass, they're attracted due to the gravitational interaction. Then I'd put big G, mass of the first sun, mass of the second sun, it's the same, over r squared, the separation squared. But everything else would be the same. So I could figure out how long does it take the two stars to go around each other. In this case, it's an electron and a positron, but the math and the setup, the thinking is exactly the same. Alright, so I hope going through those 6 problems helped you understand the homework a bit better, helped you understand the topics covered a little bit better, and your problem solving skills. And I will see you next time with various answers to some questions from the next homework set.